And we're talking about the power quality aspects. That's, for the most part, looking at the harmonics from the input to the drive back. So if we hear about the harmonics, and I don't know if what the gentleman this morning talked about, but 60 hertz comes in, it chops it all up and rearranges it at DC bus to make some other variable frequency. But when I chop it all up, I get a lot of high frequency components, and the high frequency currents, they flow back to the source the opposite direction. Actually, they flow wherever the lowest impedance path at Ohm's law at that frequency dictates. But the harmonics on the front end, essentially for the drive DC link forward, go back to the source. And then I have the inverter that's on the output of the drive that go the other direction and flow to the individual motor on the drive. Okay? And I want to walk you through what we call sine wave filters. Why do we want to put them on? I don't know how many times people says, oh, I don't need sine wave filters. Well, I'm going to show you pictures and some real-world scenarios that may change your mind. And we'll talk a little bit about the aspects and why I need it, why I don't need it, or what are the consequences if you don't. Since you're in the oil field industry, they asked me to use a lot of the oil well examples because they're a lot of unique. How many in here have motors a mile away from your drive? Or should I say 3 kilometers? Typical oil well is you'll have the drive or the starter, whatever it is at the top, and they'll have a hole 6 inches in diameter, and it goes down anywhere from 2,000 to 13,000 feet, and the pump and motor got to go down at the bottom. Up here, it's not so deep because your oil shell, oil sands, but it's more horizontal. It may be a couple thousand feet of cable, 2,000 or 3,000 feet of cable. It may only be 300 or 400 feet below the surface. But the point is, I'm a long distance as far as electricity is concerned from the drive. As soon as I introduce that distance, it becomes a real new thing. Now the other thing is, remember, the pump and the motor, they got to fit down this little bitty hole. If I want to have a 100 horsepower motor, what's the diameter of a 100 horsepower motor here on the surface? Maybe 2 feet in diameter. How's that going to fit down my 6-inch hole pipe? The submersible pumps are narrow and skinny. Most of them 5.62 inches in diameter, 100 feet long. It's a very unique animal. So I want to show you some examples of that. But however, the laws of electricity don't pay any attention to property lines or issues. So what I'm going to show you, the only significant difference is how it affects the motor itself on a submersible, since it's a different animal than the surface, and how long the cable is. And then I'm going to look at the drives and say, how does it interact, or what does it cause the issues with the motor and the load? The bottom line is that when we go to a variable speed drive, we literally want to convert it to, we want a variable frequency pure sine wave. That's ideal. The motor wants to see a pure sine wave. So everything else we're doing is approximation of it in terms of an economic piece. Okay? Okay, well, what are sine wave filters? Why are they needed? Who cares? Well, let me tell you what, if you put a drive and you don't pay any attention to it, just went cheap and dirty on the drive, and I didn't do the system, and you look at it, in about a year, what do you think is going to happen? How many of you have seen this statement here at the bottom? Any of our salesmen in the room, you'll know exactly what I'm talking about. They're just an adder the vendor's trying to sell me that I don't need. How many times have you heard that? How many times have you said that? Okay? I mean, that's real world. I mean, I've said it when somebody's trying to sell me something at my home. Yeah, I think the same thing. Let's face it, a salesman's role is to sell you something. And your job is to make sure you only buy what you need. So that's the issue. But I want to show you on the technical ones. If you don't care, that's fine. But the symptoms are, after about a year, your bearings are shot. You're replacing motors or bearings. In about 2 months, if it's really bad and you didn't do a special motor, you're blowing up the interns on the insulation on your motor. That's a surface motor. If I'm a submersible pump, there's a step-up transformer frequently in the smaller ones. You fry eggs on the transformer, it lasts about 3 months. The motor lasts about 3 months, and your pole costs go way up. The connections and the cable to it get hot and burn up. These are all symptoms of it. Because bear in mind, when I'm looking at a drive on the output, I'm looking at high frequency superimposed on top of the 60 or 25 hertz or whatever you're running at. and the high frequency aspects of it behave dramatically different than the fundamental frequency. Okay, let's talk about some of the drives. You have to understand how the drive makes the output. So when you hear a drive, you hear things like a voltage source inverter, current source inverter, older technology we call 6-step. They're almost always talking about how the output of the drive generates or approximate the voltage to feed it. Okay? A voltage source inverter we call VSI or CSI. The vast majority of the drives made today in general industry are going to be VSIs, voltage source inverters. They control the output voltage and frequency and allow the motor to draw whatever current it needs at that frequency and speed. The speed of the motor is going to be proportional to frequency, and obviously the faster the motor turns, the more torque is on the shaft and the more load the pump or whatever the mechanical load requires. And it's going to pull however many amps at that voltage and frequency that the motor dictates to do the job, keep the shaft turning. A current source inverter is the opposite technology, less like a Chevrolet and a Ford. They're both cars, they both go to point A to point B, but they do it differently. Or a hybrid's may be a different one. One gets you from point A with batteries, and the other is more conventional gasoline engines or diesel engines. The current source inverter is just the opposite of the voltage source inverter. It controls the output current and frequency and lets the voltage be whatever it is over the impedance or the ohms of the load. Now, it's also a function of what the voltage coming in is. I mean, if I feed this current source inverter 2,000 volts and it's rated 4160, I'm not going to get 4160 out of it. It can't generate voltage. But it will give you a voltage range of maybe 25% plus or minus based on what I want to do on the output in the full frequency range, where a voltage source inverter can be 25 or 10% if you want to, all the way up to 100%. Okay, now any of you here in the oil patch, the oil fields? Okay, do you have any of the Baker Hughes central lift drives? Okay, they're 6-step, which is square wave outputs like they did in the mid-'80s. They're the only one in the world that still make 6-step. And I'll show you a little bit of those because some of you will probably have them because of oil fields. Since this audit, none of you have the 6-step, I'm just going to touch on it briefly and move on. I'll focus more on the VSIs and the current source inverters and medium voltage equivalents. Okay, let's look at the waveforms, and this is just a first pass to give you a concept, and I'm going to go back. If I look at a 6-step, here's the voltage. You see the 1, 2, 3, 4, 5, 6, and I'm ready to repeat. Now, it will be actually out of the drive on a phase-to-phase, it will be square wave like this and another one like that. And when I go through this delta Y step-up transformer and the oil fields, it shifts it from the square wave to this wave. But they're really referring to what the voltage looks like on the 6-step. That's a 1985 technology. Everybody's drives from the 80s look like this. And with that square wave voltage, what's the current going to look like? All those bumps, it's got a lot of low frequency current. The PWM, pulse width modulated, that's the vast majority of voltage source inverters sold in the world today. They all use some variation of this, and what they do is they rectify the current from the front end to be a fixed DC bus. Then they have a lot of high-speed switches, and if you'll notice, each sliver of voltage is essentially the full DC magnitude, okay? And then the question is how wide is it? So what you do is you have a little spike here, and it looks like it's not there, but that's just the measurement accuracy. If you notice the first part of the wave, here's a square wave like this. That would be 6-step if I were back in the 85. But if you notice, the magnitudes are the same on all of it, but there's a sliver of voltage, then it turns off, and then you get a little wider sliver of voltage, a little wider sliver of voltage, and then in the middle is a big wide piece, okay? And the wide piece is that, and the area under each little individual surface, when you add it all together, allows you to approximate a current like this. It's a sine wave. So if I look at all the time it's on and average it, it will be closer to a sine wave voltage than this is, okay? Now, when I do that, the current starts flowing a little bit here, and then it goes away, and then it goes a little higher and a little bit, and you end up with a current looking like this. So the current going to the motor is much closer to a sine wave than here, with one exception. If you notice the high frequency content. The high frequency content is due to what? The carrier frequency. How many times per second does it turn off and on? Okay, I don't have the lower order harmonics, but I got to deal with the carrier frequency. And I'll show you what that means. You'll have multi-level PWM on the market, and that has a whole lot of 480 volt units put in series. So collectively, they all add up with all three phases, and they'll get 4160 or 6900. But I have a whole lot of small low voltage elements built in, and I'll show you how that's done. Just different ways of using the same technology. The current's even smoother on the multi-level to the motor, but look what the voltage is doing. It's better, but it's not perfect. And obviously, what's all the frequency of that high frequency hash? Carrier frequency again. Now, what is carrier frequency? How many times you turn the voltage and IGBTs on the inverter on and off per second? Now, the higher that carrier frequency is, the smoother the current. But what's the trade-off? The more of this high frequency hash, the more heating downstream. And in fact, in most IGBTs, if you run the frequency too high, you have to thermally derate the IGBTs because they get too many heat losses. So this is part of the trade-off in the drive. For most motor applications, especially in the oil field example, 2,000 to 3,000 hertz is the ideal carrier range. I go dramatically less than 2,000 at low speeds. I'm getting jerky, things like this. And at the high frequency end, I'm burning stuff up because of the skin effect heating and the eddy current losses at the high frequency. Okay, let's look at it. Let's look at the basic building blocks of a drive. The front end, you're going to have a rectifier, and it may be SCRs, diodes, different manufacturers. Okay, you'll have a small inductor. Sometimes you have one here, sometimes you don't. With a great big capacitor. This is a voltage source inverter showing the technology. Then you'll have 6 steps of output, and the symbols are a little bit different, but am I using IGBTs or GTOs? There's different manufacturers do it a little differently, and then and even on the inverter, then I go to the load. So I got a rectifier, I got a DC link, and I got an inverter. A voltage source inverter is primarily a great big capacitor, huge drawer full of capacitors. Here's some real measurements. And if I look at this, a little sliver, it's off, a little wider sliver, a little wider sliver, a little wider one, it gets thicker in the middle and it goes down. Then it does an identical pattern upside down at the opposite polarity. So I'm approximating that voltage waveform. This would be a line-to-line magnitude. Now, if I look at the harmonic spectrum of all this pulsing stuff, the THD is 72%. On a low carrier frequency, so it can be very severe on the voltage. The 13th, the 17th, the 31st, but if you notice, I'm getting some very appreciable high frequency content. And you get one way up here in the 30s, I'm going to say the carrier frequency is very close to the 29th. See how big the 20, normally if I look at harmonic distortion, once I'm above 13, it's very small magnitudes, not in the drive itself. Okay. Now, that was theory. What you have here is real-world unfiltered PWM output that's going to a motor. This is a 30 horsepower 480 volt motor. And if you'll notice, you'll see the line-to-line voltages. Here's the 0 point. This is 1/2 square wave. This is the other half square wave. And you'll see it. Now, there is a little bit of difference. I showed you the theoretical max and how it was built. What's all this stuff right here? Up on top. It's supposed to be that magnitude coming off the drive. Why is it higher? It's higher because of what we call reflections. Okay? When I deal with electricity, we follow Ohm's law at 60 hertz, and still Ohm's law still applies. But once I start getting relatively high frequency, the laws of electricity behave dramatically different. The analogy I use is when I was a kid, I used to love to throw rocks in mud puddles and watch the waves go out. You know, just drop a big rock in a mud puddle and you get a traveling wave in the water, it goes out. What happens to that wave when it hits the edge of the mud puddle? It momentarily doubles, goes to 2 times the magnitude, then bounces back on itself. Laws of electricity follow the mechanical. For every law in the mechanical realm, there's an equivalent one in the electrical realm. I'm turning these on and off so fast, I'm now evoking the lightning type protection characteristics of inductors and transformers and stuff. And these are reflections bouncing off the motor coming back. Okay, now look at the current. Here's the current. If the carrier frequency is doing this in the voltage, what do you think the current's doing? Now, that's the fundamental. Okay? What's the frequency here of all the stuff on top of it? The same thing as harmonics, except for what? It's at the carrier frequency. And if I look at a 480 volt, 600 volt drive, this is unfiltered PWM like we use everywhere, and I put a power quality meter on the output, this is what I'm looking at. Phase-to-phase voltage and line current. Okay, now what we don't look at is they never look at line to ground. They're ungrounded outputs. I'm showing you the line to ground output. If I'm doing all this on the phase to phase, what do you think's line to ground? Same carrier frequency, but if you notice this on top, that is a huge third. That's another reason you don't want to solidly ground the output of the drive, because these thirds will take all the energy in the third harmonic at 180 hertz and burn everything up. However, the reason I'm showing you this, because there's really 2 problems you have with drives if I do not filter them. Actually, several. One is at the high frequency on the line basis, I'll get a lot of excess thermal heating because of the high frequency, and I'll show you why in a minute. And if I have a lot of a high frequency line to ground, the line to ground couples onto the rotor through induction like a current transformer and induces just circulating high frequency currents circulating between the rotor and the stator bearings, and it burns up the bearings. It's called fluting, F-L-U-T-I-N-G, and the line to ground waveform is what drives the fluting. The phase to phase drives the high frequency current, the skin effect heating, it all gives you an impact. Okay, let's look at it on the good part. It's relatively sinusoidal compared to the 6-step before. The current waveforms without filtering, I showed you. They are very flexible. You can run at very low voltage and frequency. If you have no idea how much I need, I could actually run your drive at 15% voltage and frequency. Now it's not going to be anywhere near efficient. The drive is not real controlled, but I can make it work. Okay? It has significant stored energy for voltage sags. For example, if I'm remote in an area and lightning hits a line or a tree falls on it, the voltage drops down to 80% for 0.5 seconds while the fuse clears. The stored energy, that just keeps the drive right on rolling. If I have a current source inverter with an inductor to store the energy, after about 1 or 2 cycles, your stored energy is gone, the drive turned off. So it rides through your remote areas. That's a good thing. It's easily applied sine wave filters due to the high carrier frequency. On the low voltage devices, I can run my carrier frequency in the 2-3 kilohertz, 2,000, 3,000 hertz range, and it's much easier with sine wave filtering to fix it, and I'll show you what I mean by that. What are the problems? The voltage reflections of the motor due to the high frequency. Fluting, we'll show you that. You may have to buy inverter duty motors so the motor survives. You cannot do that at a submersible pump. When I get to the pumps, I'll show you. Okay, let's take the modern technology and let's say instead of a 50 horsepower, 100 horsepower drive, I now want a 4,000 horsepower drive. We're starting to get quite a bit of them in other circuits today, right? Well, how do I do it if I'm using the multi-phase? It's one technology, a way of doing it. Well, this is a 480 volts single phase 6-pulse PWM element. 1, 2, 3, 4, 5. 5 times 480 is 2,400 volts. Do the same thing, 2,400 volts, 2,400 volts, 4,160. So I just put a whole bunch of 480 volt off the shelf, easily applied IGBTs and circuits that's out there by the thousands in the marketplace, and I very carefully put them together to make it a medium voltage drive. Okay? That's how they build it. Now, if I look at it unfiltered, what does it look like? Bear in mind, since I've got so many low voltage individual modules with that technology, I phase shift the carrier frequency so the reflections are proportional to 480 volts now, not 4,160. So the reflections are much less. If you can see them here, see this is 4,160 basis, Actually, it's operating at 52 hertz. But it's there, but it's getting closer to a sine wave each time. This is an unfiltered PWM drive. This is actually about feeding a 750 horsepower motor in the North Sea in an oil platform. Okay, and if you look at the current, it's a lot smoother. You don't have all the high frequency. This is about 8% total harmonic distortion. But if you notice, there's very little high frequency in the current. Okay, let's look at the multi-level. What's good about it? It's cost-effective for high horsepower, medium voltage applications. It tends to have a very good power factor. That's good when I'm buying for the power company, so I don't have a whole lot of watt or VAR losses. It has low output distortion for the most part, and I say low, that's compared to the other technologies that are unfiltered. It uses low-cost, low-voltage components. You can buy medium voltage drives with 4160-volt rated IGBTs. Well, they're a lot more expensive. You don't have a whole lot of them and the like, but it's an issue. It requires special input transformer. If I got a whole bunch of 480 volts to get 480 in the drive, I got to have a 9-phase or 18-phase special transformer in the front end to help me build all those secondary voltages. And it has minimal voltage reflections compared to the other technology. What are the problems? Generally, it's a sophisticated piece of equipment. It's an indoor application only. You're not going to get an EMA 3R. You're not going to put it out in an oil field up in the oil sands in Fort McMurray by itself. It's not something you can put out by itself. You have to build a house around it. It does not preclude fluting or eliminate fluting, and it still requires sine wave filters if I have fairly long cable runs. It doesn't need them anywhere near as much as the other drives, but it gives you some idea at least. Okay, let's go to the current source inverter. Current source inverter, it's the same concept, rectifier on the front end, DC link, but if you notice, there's no capacitor. It stores its energy in inductors, and I use it to smooth, and I have my inverter, and out to the motor. Now, they almost always have capacitors, power factor capacitors, but if you notice, they're not filters. Well, by default they are. They're going to cause some issues, and they may filter and or amplify depending on how much cable and what the motor size is. The nice thing is, though, it doesn't really amplify the issue. Okay, what's good about the CSI? It's a simpler design, and that generally transmits to a smaller footprint. If I'm on a platform in the North Sea, every square foot of platform space is $250,000. So, you know, your savings may not be in the drive, but in the platform or the building or whatever. It gives you a cleaner output waveforms. I say cleaner in terms of high frequency. It's low frequency harmonics, okay? It has lower distortion, maybe. It injects a certain amount of harmonic distortion and of current to the load. And the voltage distortion, obviously, is a function of what's the impedance of that frequency, because it's going to force the current out to the motor. And whatever the impedance is going to be the voltage distortion the motor sees. You don't need a special input transformer. They're most of the time at medium voltage. Well, you can have small low voltages. If you go back to the 1960s, almost all drives were current source inverters. And you'll have a decent input power factor or better than some of the others. What are the problems? The limited voltage range. At the rated frequency, I've got to be about 75% to 100% of whatever the output rating is, or I'm outside the voltage range. Remember, if I feed 4160 in, I get 4160, well, 3300 to 4160 is the only voltage range that I can tweak the controls and get. If I wanted to run a 2400 volt motor at 60 hertz on the drive, I can't do it. Where the voltage source inverter gives you that flexibility. Now, as a normal, you could design this up front, match the drive to the motor and so forth, and that can be a limitation that's not a problem. In the oil fields where they change the motors every 2 or 3 years, and this is what I have, and the voltage ratings are all over the map, very frequently they don't match. So you have to be more limited. It doesn't have anywhere near the energy storage to handle sags. If I'm up here in the oil sands where you're prone to very inclement weather in the wintertime, if you have a lot of aerial lines feeding power to them, lightning strikes, tree limbs, all that sort of thing, you're more prone to it. And when you get that voltage sag, the voltage source inverter rides through better. Okay, you may require output capacitor, sine wave filter, power factor correction. Almost all of them I've seen in the larger size will have power factor correction capacitors only. Here's what the waveform looks like on a CSI going to the motor. You don't have the high frequency content, but it's not clean. I mean, you have maybe about 10 to 12% total harmonic distortion. Now that's getting a lot closer to the waveforms. This would be the voltage, and here are the three currents, okay? But it's still within realm. It's not bad. Okay, let's look at the current. So this is the voltage harmonic distortion. If you'll notice, this is ABC output. This is the frequency is 8.6% THD. So this is the current source. Now the voltage was pretty clean. All right, now let's go to 6-step. This, if you had a 1980s drive, this is the line-to-line voltage on the output of the drive. If you have one particular manufacturer. But if you notice, when I turn it on instantly, whether it's a 6-step, you see the ring going on. Now the reason it's not more pronounced is on this one is that I was not in high-speed transient mode on my meter. It was a slow-speed capture, so it didn't capture all of the high-frequency event, but you'll see it happening. You still have that. It's just not huge. Here's the current. That was very typical. This is 35% harmonic distortion, huge fifth. This particular one, you see the ring wave right here? I'm turning off and on that square wave, and it's ringing and resonating at the 71st harmonic in this case going down hole. This is a prime example. This is out of Virginia Hills. Okay, you see that particular current waveform. You see this high frequency ring? Every 6 months to a year, they would be burning up their cables going to the downhole pump. Now, bear in mind, these cables are probably 4,000 feet long, but you got to get a workover rig out there and pull the pump to get to the cable. So it's what, $50,000 workover rigs in the mid-90s when I did this, and all that says is let's just detune the high frequency resonant of it. What are the problems? Just to give you an idea. I'm not going all of them. The PWM, the multi-level has the least, but the multi-level is a more complex animal. And you almost have to be in the 300 to 400 horsepower size or larger for the motor before it's economical to go to the multi-level. Okay, and again, you got to factor economics into which technology. Each one's got a problem. There's only one manufacturer left in the world that I know of that's still building 6-step today. Okay, let's talk about the step-up transformers. And since I was asked to talk about the oil patch because we're so close to the oil sands here, most of the drives for the submersible pump, since the distance is so far away, I may only be an 84 horsepower motor, but I'm 3,000 feet away. I can't run 3,000 feet of 480 volt or 600 volt cable and have enough voltage to run the motor. So they're all in the medium voltage range, anywhere from 1,400 volts to 4,600 volts. Now you'll get 2280 volt, all kinds of weird voltage ratings on the motors, but because they're so far away, and it will be at a higher frequency. But let's look at what's the resistance of the step-up transformer. The drive is probably 6-step or PWM or whatever at 480 volts, and they have a step-up transformer with 20 taps on it to give me whatever voltage I need to send down hole. That's been around for 30 years in oil patch. So I got a transformer involved. Now, when I have high frequency with transformers, there's skin effect and eddy current losses. Eddy current losses follow this equation. There's a DC component of the resistance. Now, bear in mind, I'm looking at whatever 100% of the resistance is for the windings in a transformer. So it's going to be different by design, but whatever that transformer is, I'm going to say that's 100% of the resistance at 60 hertz or 50 hertz, whatever your test value was. And if I were to check it, if the equation is a DC resistance plus H squared, that's a harmonic squared, times whatever the 60 hertz resistive component is. And for most transformers, if I did a 60 hertz test, 90% of the resistance is DC, 10% is eddy current losses. Now, if you'll notice with 0.1 here, and 0.9, and H is 1 at the fundamental, so 1 squared, there's my 1 or 100%, 1.0 times whatever the 60 hertz value is. Now, let's say I pump a bunch of fifth harmonic current through it. Well, the fifth harmonic follows the same equation, but it's the RDC plus the H squared. So it's 0.9 plus 5 squared times 0.1, 3.4 times. So I don't have to put a whole lot of fifth through that transformer to make it hot. And if I do the 11th, it's about 12 times. Now, if I don't filter the carrier and do unfiltered PWM, the carrier frequency is like 2,400 hertz. So 2,400 divided by 60 says H is equal to 40. Look at the resistance of the transformer at the carrier frequency. How many amps at the carrier frequency do I have to run through that transformer with that resistance before the I squared R heating losses in the transformer burn it up? I don't know how many times I've had people come to me and say, the transformer is screaming, the paint's blistering on it, it's bulging with the oil because there's so much pressure inside. And I say, you have an unfiltered PWM, go to the motor. He says, how'd you know that? Here's why. Now, said that for the transformer. I use the transformer example but for this industry up here, but it's easy to illustrate. And the reason I did it because I remember the numbers in my head. Now, if I look at the motor, instead of 10%, it may be 7%. It's the same concept, it's slightly different percentages, but if you'll notice, the whole concept is identical. So if I run unfiltered PWM to my submersible pumps, I don't have to have much of that high frequency current before it's going to do what? It can include very easily a whole lot of excessive heat, or more heat than you're expecting. Okay, what are the limitations on the motor? Thermal is skin effect heating, eddy current losses, with the eddy current being the bigger piece. You have impulses, reflections. I showed you what happens. Theoretical max is 200% of what of the impinging wave. So if I hit a 480 volt impulse on the motor, it's going to, on the front edge, slamming into the motor, it's going to be 2 times 480. 960 volts, or slamming peaks on the end of that motor. And it's going to be doing it 2,400 times a second, 24 hours a day. Now, the insulation withstand for the equivalent of BIL will be maybe 2 or 3, 4,000 volts, but that's a one-shot rating. What do you think is going to happen if I keep hitting it time and time again 24 hours a day? It's what I call the hammer effect. If you have a hammer effect, you take a piece of steel and slam it, hit it as hard as you can with a hammer. And you look at it, you don't see anything. Steel's going to not really show it. But if I keep hitting it, and after 20, 30 minutes, you start to see little marks in the steel. If I do it for 24 hours, it's starting to really get fatigued, and next week I can actually eventually fatigue the metal and cause it to break. That's what I mean by the hammer effect. So I have to deal with impulses and reflections. I either need to make sure I don't have any high frequency for this to be a problem, or I must beef up the motor insulation to be able to withstand a whole lot more. And I have to deal with bearings and fluting because of that line to neutral high frequency issues being induced through the bearings. And then you're going to have your standard THD for voltage and current and the like. Okay, let's look at the power system responses. I look at the motor, okay, and then I looked at the drive. Now, what's going to happen in the power system, the interaction between the two through the cables, if there's a transformer on the team, what's going to happen to the transformer? Well, I got the hammer effect on the impulses due to PWM on the transformer and the motor. The reflections and the ringing, because remember, anytime you kick something, you excite the natural frequency of the system. Hit a big bump on your car, what does your car do? Take your shock absorbers off, and what does it do? It goes like this once or twice, and the shock absorbers absorb all that transient energy, and it's gone away. If I don't, it'll just sit there, and eventually, if I don't have shock absorbers or they're shot, you get major bumps and actually can cause you to lose control and crash your car. That's the mechanical equivalent of what I'm talking about. Harmonic resonance, remember, I may have long cables, or if I get the carrier frequency or just right on the output of the drive at the high frequency, I can resonate and amplify the harmonics going to the motor. Now, we talked about amplification a little bit this morning in the harmonic mitigation piece. That's at the 60 hertz back to the source. Same concept applies, just I'm going to the motor and it's not fixed frequency. It may be fine if I'm running at 55 hertz, run it up to 68 hertz on the motor. And I'm now just moved into the resonant point. A good example of resonance is on your car, and I use this because I have a lot of people that aren't necessarily in the electrical realm, is don't balance the tires on your car. At 45 miles an hour, the car is going smooth as can be, and about 55, it starts doing like this, and 65 to 70, it goes away. You're mechanically resonant at 57 hertz, or miles per hour. Well, the same thing here as I go to resonance. At maybe 55 hertz, I'm resonating and amplifying the harmonics just right down whole, and I'm blowing up motors. And you have to understand when I do that to the motor, it's not just the connections, but I get pulsing torques on the shaft too. And I'll really accelerate wear and tear on the bearings. Okay, let's talk about those reflections. I'm looking in this case at the voltage output, and I did a real high-speed transient. Here's my 6-step. Now, nice about 6-step, I only get 2 of them per cycle instead of 2,000, so it's more noticeable. Here's my 480 from here to there. There's my 200% reflection. Okay? Here's this way, opposite was 100%. These are all the reflection pieces. And every time I do a major impulse. Now, if I blow it up, that's ringing, the ring wave. And I'll come back and show you that in a little bit more detail. The voltage source inverter, the filter design, because the point is I need to do a sine wave filter on the output. What do I got to do? Well, here's the things I got to make sure works. I cannot draw excessive harmonic currents. Otherwise, all the energy out of the drive goes into the harmonics. It doesn't get it to the motor to do energy. I cannot resonate or amplify. I got to stay away from the resonance conditions. I cannot have excessive voltage drop across the filter, or I don't get enough voltage to the motor. I need to trip the VFD if the filter malfunctions. Remember, it's in there taking the high frequency stuff off. If I blow a fuse or blow the capacitor filter or something, that needs to turn the drive off so I don't burn my motor up. And it must be sized to be series resonant above the expected load harmonics, but way below the carrier frequency. And I'll show you what that means in a minute. Okay? We're going to do Bode plots. That's a fancy word. Sometimes you need common mode filters, and we'll talk about that as well, and you may need force cooled. The reason I say that for the filter, when I'm doing that high frequency, there's a lot of heat in the reactors and the components, and I got to get it out. If I'm open out to air, it's no big deal. If I got it in a confined space, I got to put fans on it so it doesn't burn up. Okay, let's look at a Bode plot. This is just a straight one, and this is a Bode trop is 20 log to the base 10 of the V output to the V in. In other words, voltage into the filter versus what goes out. And what it typically is a series reactor with a shunt RC leg. In other words, here's the path for the filter. You got a series inductor running 100 amps load current, whatever it is, and I got a small capacitor bank and shunt with it, like a power factor capacitors, and I have to put a small resistor in series with it so I don't get instantaneous overcurrent tripping on my drive. And here's the thing, I'm operating up to say around 60 hertz. So if you notice, the L to C is selected so I have almost no voltage drop across the reactor if I do it correctly. I don't have voltage drop. So whatever the voltage is on the output of the drive, on the other side of the reactor 5 feet away is within a few percent. So I'm operating here. Now remember harmonics coming out of the drive, fundamental of the 5th, 7th, 11th, 13, like 5 times 60 is 300, 7 times is 720. We're all in this range here. So I got to make sure that the normal harmonics that you may get are way below whatever I'm doing. And I take the L and the C to be resonant somewhere up in this range. In this case, 1,000 hertz, and about 3 dB down, which is about here, is the carrier frequency. So I got to be way below. Now, if I get real close to the point where I'm in series resonant on the L and the C of that filter, you'll get big amplification, up to 10 per unit. So what does that mean? I got to make sure that this frequency is way above the harmonics generated by the drive, but way below the carrier frequency, because I don't generate any harmonics in this arena. So it doesn't apply. So I got to take the Bode plot, which is a dB log, and I look at the filter, the carrier, the drive, the cables, the system, and I have to design it so that it matches the system and I don't end up with this. If I just arbitrarily buy one and just slap it on every driving system, this carrier frequency may be down here. And then it blows up. Here's a sine wave filter performance. I say average, I had that mixed company. I think it's a horrible filter. This is the voltage. I'm not doing, and I've got that carrier Bode plot too low, so you see that I'm amplifying probably the 11th or 13th harmonic. But it's not so big that it's wreaking havoc. And the current's closer, so yeah, this was a drive with current voltage that had been operating for some time. This is not ours, by the way. I wouldn't claim fame to it, but it's there. Here's what it looks like. Here's a particular one. This is a VSD. This is my filter, sine wave filter at 480 volts. Here's a step-up transformer. Okay, and here's the cable to the motor. This is a submersible pump. That's 360 horsepower load. And we actually went out and looked at one. They were having filter problems with it. I looked at it on the drive end without the filter for this particular one, and you see on each impulse, the impulses on the sine wave filter, look what's happening. That ring wave issue, here's zoomed in. What do you think that's going to do to your step-up transformer? They'd operated it maybe 10 or 15 minutes, and it was getting pretty darn hot. Because remember, this is at the 2400 hertz carrier frequency, or 3000, and it's going to 200%. You don't want to do that. Now, here's the A to B voltage with the sine wave filter and the exact same one. You notice all those ring waves just went away, all those impulses, square waves, and the actual voltage is now almost a pure sine wave. And if you saw how the distortion you had on the other one that's 480 volt hertz, look at this one. That's because this was ours, and I was involved, and I make sure the Bode plot for the drive matches. I just don't pick one of these and one of those and slap it out into the field. Okay? Here's the current going to the motor, almost no distortion. It was probably less than 5% harmonic distortion, where it was in the 35% before, and mostly high frequency. Now here's another one. This is a SAC-D well. Steam assist gravity drain. I had to ask my oil field customer that. Essentially what they're doing is up in the oil sands where it's too deep to excavate, what they do is they drill 2 holes down into the sand about 1 meter, 2 meters apart, and they run steam in the top one, so it gets pretty darn hot downhole, and that's to melt the tar so it's liquid enough, and about 2 meters below it is the second well with a pump, and it pumps it out when it's hot. But what does that tell you? Well, you're probably running at 250 to 270 degrees Fahrenheit because of the steam. Doesn't take very much load, electricity at this high frequency crap. Well, this particular site was actually up in the Fort McMurray area. They only needed about 40 horsepower of load, but they put in 85 horsepower motors because I didn't want any thermal heating, because I'm already at, the insulation's rated at 300 degrees and I'm running at 270 just because of the steam. So and that was a good sign. Okay, I don't want to have any significant incremental heating due to electricity. Here's your 6 pulse at the surface. These are actual measurements. Look what the unfiltered PWM, what it's doing on the frequency. They lasted about 3 months. The paint was blistering on the step-up transformer, and the transformer was screaming. It was so loud. Then what we did, we said, well, you can't do that. We ended up, and if you look at the voltage distortion, 34%, and the current was 25%, but the distortion is all high-frequency content. And remember what I showed you on the resistance is going to be at the high frequency? Okay, in this particular case, we put a sine wave filter on, and it went to about 7.8% on the voltage and the current. Now, about 3 weeks later, the supplier came back to us and told us the motor was running 25 degrees C cooler. They had downhole sensors sensing motor conditions, temperature, pressure, etc. And they were able to increase the frequency 3 or 4 hertz and get more production out of it. And the transformer quit screaming, and a year later it's still operating instead of 3 months. So you look at your application, it can make a sense. In the submersible pump world in the oil field, I will not put an unfiltered PWM motor on anything downhole. Every time I've seen it done, there's been a problem, or it's extremely short run times. And mainly it's because of the long cables. You're not doing 100 feet or less, you're several thousand feet. You've introduced a step-up transformer on the smaller horsepower. Even at medium voltage, you may not have the step-up transformer, but again, I got long cables. I'll show you the fluting piece in a minute. Okay, this is what the 480 volt filter looked like. Here's my capacitors. They're using 2 reactors in parallel to get the right L in a small box. Smaller sizes would do it a little differently, a soft-to-shelf design. The unfiltered PWM, the step-up transformer was screaming hot. The end user didn't say, well, it was warm. course, he had his hand on it in February at Fort McMurray. Well, yeah, it's minus 25 out, okay? Yeah, it's going to be running cool. You got the best thermal cooler I can think of. It's called the air. But I told him, he says, you know, come June, that's going to be frying eggs on top of it. Didn't make it to June. May, he was calling us up and says, this is so hot, you're blistering the paint on the transformer. So that's when we started doing the scenario. Right now, the motor's still running 1.5 years later. They wanted to get, they were going to be happy with anything over a year, and they were getting between 3 and 9 months in this particular one. And I took them for the distortion down to like this. So if you give you an idea. Now, on surface motors, it can do the same thing. What does the fluting look like? Now remember, fluting is not the high harmonic distortion. It's the real high frequency content. So the magnitudes are very small. But it's that line to neutral component at the carrier frequency that's, you just look at the motor, and I got a phase down there, and I've got, look at a current transformer. Current comes in the middle but doesn't touch the secondary. It's induced in the iron circuit, and you circulate current through the secondary CT winding. Okay, let's look at the motor pretending it's a CT. I've got iron, right? I've got primary windings that's going through the middle. We call it the stator windings. And then the secondary is just a shorted turn between the rotor and through the bearings and a shorted circle. It's like a poor man's CT at high frequency. So what happens? I start getting maybe 1 amp, half an amp, continuously, little high frequency spitters across the bearing. This particular case is a submersible pump. You see all this little bitty hash here eating the bearing? That's where the sealed part on is sitting there arcing at high frequency across the bearing. I'm inducing it. Now here's the other thing. If you'll see all the interns here disappeared. Remember I got shorted copper turns inside the winding to make a squirrel cage on the motor? A submersible pump is oil filled. Okay? It's oil filled, so at 60 hertz, the oil is a very good insulator. But when I put the frequency across that oil at 2400 hertz, it's 1/40th the impedance because the ohms of the capacitance is inversely proportional. So since I'm in an oil bath, I'm also currents coming off the interns going through the oil in the environment to the case, and it's slowly eroding all the copper and stuff off the interns. And eventually there's not enough copper and you open circuit the rotor, then you can't even start the motor. How it shows up. Here you can see it on, pull this back and you can see it inside what's happening there. Okay? Here's a surface motor. Well, bear in mind I'm full of oil, grease. And the grease in this ball bearing type motor, you can see the fluting here. This is a surface motor where the fluting's showing up. And if I haven't addressed this at all in my design, about 1 year later, you start losing bearings. This is fluting. You have to bear in mind, I've got lubrication called grease around the roller bearings, just like the oil in the intern, but instead of going from the stator, or excuse me, the rotor to the ground, it's going through the bearings. Okay? Now, what happens, so this isn't actually the multi-step waveform. Here's a 63 hertz operation. You can see the high frequency. This particular submersible pump was eating bearings. They lost 7 submersible pumps last year due to this problem in the North Sea. It's $2 million each to pull it up and change it out. Forget about the cost of the motor and lost production. The workover rigs just to pull the motor up in the North Sea is $2 million. So they lost $14 million last year. I blow it up, you can see the high frequency. Now this is what's driving it. Now from a voltage standpoint, I don't have the reflections to deal with. That part of the equation is not it. It's just it's causing very significant fluid. We actually did some other measurements. They had 3 to 4% voltage at the 71st harmonic that's driving about 1 amp of 2400 hertz current downhole and into the bearings. And after I put the filter in, you see all that high frequency went away. I'm actually down about 3 or 4%. Now there is a little bit of low frequency right here. What's that due to? Remember that hump in the Bode plot? I have a very small amount of 14th harmonic or whatever in the waveform that's right at the Bode plot. It's so small that it's not much, but I'm getting a little bit of amplification. So that's the reason being very careful how you do it makes sense. This put it all the way down. It literally took everything out. There's the sine wave filter capacitor. That's all the high frequency crap I'm sucking off of the drive and sticking into the capacitor so it doesn't go down to the motor. And that line-to-line voltage when I zoomed in. Remember, I had them a whole bunch of cycles scrunched together, so it looked real bad. Although the peaks, when I spread it out with one cycle, you don't have much at all. So you saw all that high-frequency stuff is essentially all gone. The current improved too. We'll talk about that. There's the harmonic profile. The voltage is went from 8 to 9% down to 3.8%, and the current was about 8%, went to 6.2. I thought that was terrible. I wanted to get down to about 2 or 3% on the current. Then I went back and started looking. These particular motor pumps, we actually ran a test with the motors at 60 or 50 hertz straight off the grid. This was done in Aberdeen, Scotland. And with the pure sine wave feeding it, I drew 8% distortion because the anomalies of this particular motor manufacturer drew about 8% fifth harmonic just to the iron circuit all the time. It's a phenomenal, it's a part of their rotor iron design that I can't change. So I actually improved it. If I didn't have their anomaly on their arms, I would have been down to 2 or 3% range. But remember that iron, because of their design, has to draw that current or the iron circuit doesn't work properly. Okay, the sixth step, again, you'll see a little bit of waveforms. Here's the ring. That's what you see if you have those. There's the resonant frequency where I'm resonating. It doesn't do it as much every cycle. It does it maybe 6 times a cycle instead of continuously because of the sixth step, but it's still there. If you look at it, here's all the 3 voltages, blue, and then red. So if you look, all 3 phases on top of each other, it's plus and minus, and they're just switching back and forth to get your frequency. But if you notice, when this turns on, this phase, I get a ring wave. When this one turns on, I get a ring wave. This one turns on, I get a ring wave. So you see how each time I'm going between the phases, I'm impacting the current. So I wanted to show you how that there's a cause and effect for everything. And if I turn on too fast, remember one of the basic laws of electricity. Thou shalt not change current instantaneously in an inductor. I'm trying to do that with my power electronics. And I don't care if I'm 6-step or PWM. When I do that, I invoke all those switching transients, that high frequency stuff, the ring waves, all the things that go with it. Now, if you notice, when I do the sine wave filter, I filter almost all that high frequency out, so it's not an issue anymore at all. I'm not going to do much about this. The pulsing torques have to do with the harmonics in the lower order to give me a thing where I sit there and I'm doing this all the time. The shaft couplings and the bearings are they're electrically induced, but mechanically wear out very quickly, and you think you got a bad bearing. Now, where it really is prevalent is going to be in the 6th step. Nobody's using a 6th step in the room, right? So it's going to be a small problem unless the drive gets way out of balance. Okay? Here gives you an idea, neutral to ground on the 6th step. Here's the high frequency. That's can cause fluting. It's only 40 volts, but it only has to be maybe 0.1, 0.2 amps continuously. That over 6 months or a year, I start eating my bearings up. It's funny, we actually did this on a 6-step drive last year for an oil company up in North Dakota, and I'm almost done. And they couldn't keep this well on hardly at all. It was just eating their lunch. And then we finally put the filter on. We did the grounding, made the power quality signal and everything right, and the drives and feeding the motor. And we left on a Friday, and the next Tuesday or Wednesday, the customer called us back all excited. He says, the drive only turned off once this weekend. We thought, well, why did it turn off? Well, normally it turns off 7 or 8 times every weekend, and we have 7 or 8 times every weekend they got to send somebody out to do it. Well, why did it turn off? Well, the reservoir tank got full and had too much fluid in it, so it had to turn off. Well, if it's running, it's been running continuously and it turns off 6 times, I never fill the tank up. It just ran so steadily, it filled the tank up, and then the overflow valve says I can't store any more fluid before I pump it into the pipeline. You have to shut off. So that the outage actually made sense in their case. It wasn't a power quality issue. Just real quick, this is a sine wave filter line to line. This was a 6-step. This particular manufacturer put their sine wave filter on, and if you notice, it doesn't look very good, and the current's better than the PWM that they had, but actually they did another switching mode on theirs, and our power quality meter died, and we had to send it back to the factory to get fixed. So we told the customer, don't ever operate in the other mode. What I'm showing you this is, in summary, is that you need to do a little bit of engineering. Don't be afraid of it. I have some of these anomalies. A sine wave filter can go a long ways. They're valuable sources, solutions to motor applications. Your efficiencies. There's a reason you put a drive on it, because the energy efficiency or what I'm trying to accomplish. You need a proper selection for the sine wave filter. It can have a dramatic effect. I've shown you some of the difference if I just pick one off the shelf versus doing a little bit of upfront engineering. Bear in mind, the upfront engineering, what I'm telling you, you do it one time, and then for the next 20 years, it's going to be fine. Okay? The pumps have long cables. You're going to have the sine wave filter requirement because those long cables and reflections eat your lunch. Have you heard of DVDT filters? A DVDT filter is a little bitty sine wave filter on the output, and it just rounds the corners enough to get rid of the reflections. It doesn't do anything for common mode noise or pulsing torques or the others, but it's cheap. Okay? It allows you to go a little longer cables. It does nothing for fluting. And here's the thing, if I put a sine wave filter on, you don't actually have to buy an inverter duty motor. An inverter duty motor does two things. It has beefed up insulation to handle much higher reflections, and it has an insulated bearing on one end. So I've got an open circuit in that induced path for the fluting. That's fine for a surface motor with 2 bearings. Submersible pumps got 20 of them. And they're all about this big around, so it just doesn't work in that environment. So look and see what you are, what you have, and where you go. The recommendations, if it's in very large or significant VFDs, it's really important to you. I'm going to consider a sine wave filter because I want it to go. I'm not in the how much does it cost phase the first time and walk out the door because it's somebody else's problem after that. I'm always in the service end, got to make it work and keep calling me back. So my reason's a little different. If I'm over 100 feet, you should at least consider it. I mean, that's a cable from the drive to the motor. You may need to do common mode filters. What common mode filter does, it takes the line to ground or neutral to ground high frequency stuff that drives the fluting. I can put the sine wave filter and that takes care of the phase-to-phase quantities, but I need to get the line to ground because that's the fluting source. Okay? A common mode filter is a line to ground or neutral to ground filter to suck up the high frequency. And the nice thing about a common mode filter is dirt cheap. It's small. Okay? I just don't use DVDT filters. If I'm going to all the trouble to put a filter, I'm going to go put the full one in. It's best to match the sine wave filter to specific motor installation. One size fits all is far from ideal. I showed you just a one size fit all standard versus matching it. In most cases, 2 to 3 kilohertz is where I want to set the frequency. If I go too low, the exception is medium voltage drives. If I go higher carrier frequency, you may burn up the sine wave filter reactor or the motor because of the skin effect heating. You don't have the reflections issue. The current's smoother, but I have a lot higher. I remember that resistance to reactors and transformers and motors has got that H squared term in it. And don't let your price dominate. The price for the equipment the very first time pales to insignificance if I can't keep the motor running and it's down all the time. Because once you get it in operation, the importance of the drive is it. And with that, I'm 2 minutes past my time. That's a first for me. I'm normally 15 minutes or more past. Thank you so much. Informally talk if anybody wants out, but hopefully I've given you an idea. I showed you a lot of submersible pumps because it has to do that in this Iraq fluids, but same principles to everything apply to surface motors and machines as well. Just look at it and say, does it make sense or does it not? With that, thank you very much. Informally, since we're in somebody else's time, I'll talk a little bit, but I'll let you go. Thank you, gentlemen, ladies.